Hello friend, Namaskar, I am JK. In the series of cement chemistry, Dr. K Mohan sir has already tell about the proportioning of raw mix design and vulnerability of raw mix. Now I would like to request Dr. K Mohan sir to tell us about the effect of various factors on vulnerability and impact of clinker quality.
Fantastic question you have asked, Mr. Singh. It's a very important aspect. So now we'll discuss the effect of various factors on vulnerability and impact on clinker. So first, we'll discuss effect of moduli, and under effect of moduli, first is lime saturation factor, LSF. Higher LSF results in harder to burn raw mix. So raw mix become harder to burn. And higher LSF also increases C3S in clinker. It reduces C2S in clinker. There is high free lime in clinker. Because of higher LSF, fuel consumption is high. Because of higher LSF, refractory lining gets deteriorated. And there is increased radiation from kiln cell. And also kiln gas temperature increases. And unsound cement is produced. And the cement which is produced is slow setting with high strength of cement, and it improves the granularity characteristics of clinker. Now next we'll discuss silica modulus SM. Higher silica modulus results in harder burning of raw mix, high fuel consumption, difficulty in coating formation, radiation from kiln cell is high, and refractory lining gets deteriorated, and it also results into slow setting and hardening of cement, and high free lime is also noticed. Next is high alumina modulus AM. Higher AM results in harder burning of raw mix, high fuel consumption, C3A gets increased, C4AF gets decreased. Because of high alumina modulus, both C3S and C2S they increases, and more of C3S will increase as compared to C2S. It reduces liquid phase and kiln output, increases viscosity of liquid phase at constant temperature. If alumina modulus is too low and raw mix is without free silica, clinker is sticking and boiling is too high. Alumina modulus determines the role of fluxage in raw mix. If alumina modulus is less than 1.23, alumina acts as flux. If alumina modulus is more than 1.23, iron acts as flux. Now I will discuss the effect of minor non-volatile components one by one. First is free silica. So here limiting range is 0 to 3% and preferable range as low as possible. So as low as free silica is there, it is better. Higher free silica increases fuel and power consumption. It causes difficulty in coating formation. It deteriorates refractory lining, and it increases radiation of heat from kiln cell. Next, we'll discuss MgO. Limiting range is 0 to 5%. Preferable range is 0 to 3%. Higher MgO favors C3S formation. Higher MgO has tendency for boiling in burning zone. It affects kiln operation and it causes unsoundness in cement. I will discuss role of MgO and SO3 in detail later on. SR, strontium oxide, limiting range 0 to 4%, preferable range is 0.5 to 1%. Higher strontium oxide accelerates combination of CO in solid phase, lower sinking temperature, tends to release free lime by allied decomposition. Cr2O3, limiting range is 0 to 2%, preferable range is 0.3 to 0.5%. Higher chromium decomposes C3S into C2S and free lime. Then alkalis, Limiting range is 0 to 1%. Preferable range is 0.2 to 0.3%. Higher alkali improves burnability at lower temperatures and deteriorates at higher temperature when sum of sodium oxide and potassium oxide is more than 1. Increases liquid content and coating formation, lowers the solubility of CO in melt, breaks down a light phase, creates operational problem due to external and internal cycles. Then sulfur compounds, limiting range is 0 to 4%, preferable range is 0.5 to 2%. Higher sulfur compounds act as an effective mineralizer and modifier of alkali cycle by forming less volatiles, lowers the appearance temperature of liquid phase by about 100 degrees centigrade and increases ionic mobility of oxide, improves burning of raw mix of lower temperature and deteriorates at high. Then P2O5, limiting range is 0 to 1%, preferable range is 0.3 to 0.5%. Higher P2O5 accelerates the clinkerization reaction, reduces the intensity of internal cycle, reduces C3S. Fluoride, limiting range is 0 to 0.6%, preferable range is 0.03 to 0.08%. Higher fluoride leads to modification of the kinetics of all burning reactions, lowers the temperature of C3S formation by 150 to 200 degrees centigrade. Chloride, limiting range is 0 to 0.6%, preferable range is up to 0.015%. Higher chloride forms more volatiles and causes operational problems due to its complete volatilization in burning zone. Now I will discuss what are the effects of MgO and SO3 on formation of clinker phases and alite polymorphism. SO3 hindered the formation of C3S by increasing the formation temperature by 100 degrees centigrade. SO3 could promote the formation of C2S rims, indicating the dissolution of C2S. MgO enhanced the formation of C3S in both the blank and SO3 bearing clinkers. MgO favored the formation of M3 monoclinic type alite, whereas SO3 could stabilize monoclinic M1 type alite. Now I will discuss influence of MgO and SO3 on kinetics of alite formation. If the MgO content is high and SO3 content is low, alite is formed immediately after reaching the burning temperature, but with raging degrees of conversion. The rate of alite formation is decreasing. Low content of MgO and high content of SO3 delays the beginning of alite formation and increases its growth rate. At higher content of both oxides, the negative effect of SO3 on initial formation of alite is suppressed, while the positive effect of SO3 on alite formation rate is maintained. Positive influence of MgO is observed only in presence of alkalis, specifically K2O. Alite formation in high SO3 clinker with low content of other minor oxides can be entirely suppressed. The observation of the structure of burnt raw mills with various combination of minor oxide like K2O, Na2O and MgO reveal their compensation effect, suppressing the negative retarding effect of SO3 on the start of alite formation. The compensation effect decreases in the order K2O less than MgO less than Na2O. Monitoring the influence of minor oxides on formation and properties of Portland clinker is very important for investigating the influence of non-traditional raw materials, waste materials, and especially alternate fuels on clinker burning and for their optimized dosing. The above findings can be beneficial both for intensification of current production and for new production techniques. Now I'll discuss influence of SO3 on cement characteristics. Increasing the amount of clinker SO3 at low alkali level reduces the percentages of the tricalcium aluminate, that is C3A, and alite, as well as alite to belite ratio, leading to a modification in the cement. For these reasons, cement produced from a clinker containing high sulfate and low alkali have slower strength development and higher sulfate resisting level than that produced with low sulfate.
आशा करते हैं दोस्तों आज आपको अच्छी खासी जानकारी हासिल हुई होगी। अगर आपको वीडियो पसंद आया हो लाइक और शेयर ज़रूर कीजिएगा। जैसे जो भी न्यू कमर्स हैं, जो एक्सपीरियंस पीपल भी हैं और जो मैकेनिकल फील्ड से हैं चाहे इलेक्ट्रिकल फील्ड से हैं, वो आगे बढ़ना चाह रहे हैं और सीमेंट की जानकारी लेना चाह रहे हैं, सीमेंट केमिस्ट्री के बारे में जानना चाह रहे हैं, तो वीडियो को बिल्कुल मिस मत कीजिएगा। आपको इससे ज़्यादा डीप नॉलेज कहीं किसी प्लेटफॉर्म पे नहीं मिल पाएगा। अगर आपको वीडियो पसंद आया हो लाइक और शेयर जरूर कीजिएगा। हमारे YouTube चैनल पर नए हैं सब्सक्राइब करना ना भूलें, बेल आइकन को जरूर हिट कीजिएगा जिससे आपको लेटेस्ट अपडेट नोटिफिकेशन मिलता रहेगा, हमारा मोटिवेशन बढ़ता रहेगा। वीडियो देखने के लिए बहुत बहुत धन्यवाद।